Okay. Good afternoon, everyone. My name is William Chen, and my advisor professor is Mingwei Lin. And today I'm going to report about the construction of the dial-pumped ytterbium-doped calcium fluoride regenerative amplifier. And this is my outline. The first part will be the introduction. First one is why, the purpose of building this laser system, and how to construct this regenerative amplifier. Second part will be the literature review, and 我刚安白色的点 Okay. All right. Okay. And the next one will be a summary, and the last one will be my future work. So the introduction. The purpose of building this laser, well, in our future application, we will be researching. Oh, the laser pointer. Okay. So our future application will be researching about the sub-terawatt laser wavefield acceleration system, the LWFA. But I won't mention it too much today. I will put it in my future work part. So I'll first focus on the requirement of this LWFA. So we needed a laser that's the peak power of it will be around 0.5 terawatts, and the pulse energy will be 26.5 millijoule, and pulse duration about 50 femtosecond. And we'll need a oscillator to generate our initial seed light, and then it will go to our first stage amplifier and going to our second stage amplifier. Well, so how to construct this regenerative amplifier? So a regenerative amplifier, it is comprised by three different kinds of elements. The first one will be the gain medium, which is at here. The gain medium is a major determining factor of the wavelengths of this laser. And the gain medium is being excited by the pump source, which is here. It is also the place where the spontaneous emission and stimulate emission take place. And the second one will be the optical cavity. So the optical cavity is being shaped by a highly reflected mirror, about 100%, and another end mirror will be a partially reflected mirror, about 99.9%, to allow a bit of laser output to get out of this cavity. And an optical cavity allows the C beam to circulate in a closed path. And third one will be the pump source, which is the energy source of the amplifier. And lastly, the way to control the ports to get in and out of this cavity, we will need to use a Q-switch mechanism. And a Q-switch mechanism will need a Paco cell and a thin-film polarizer. So a Paco cell, it's a electro-optical device that can change the polarization of a light. And when the light is a P polarized light, it can penetrate the thin-film polarizer. And if it's a S polarized light, it will be reflected. So this is how we control a pulse to get in and out of this cavity. So also, we need to use a mechanism. It is the trip pulse amplification. So how a trip pulse amplifier function is to use a stretcher grating. So from our initial oscillator, our RC beam will get into this grating, and our pulse will be stretched to a low power pulse, because we need to avoid a nonlinear effect after amplifying, and also we will avoid the peak power too before it damage our optical component. Then we will be amplified, and this part is today I'm going to focus on. And after amplified, the energy will raise, and then we'll compress it again to be a high intensity peak power again. Okay, so next part will be the literature review. So the first one is a broadband regenerative laser amplification in ytterbium-doped calcium fluoride. So for this paper, the result is a output pulse energy about 17.3 millijoule has been achieved with a ytterbium-doped calcium fluoride amplifier. and the bandwidth of the output pulse spectrum was 7.3 nanometer, and it's being seeded with femtosecond pulse stretched to 2.2 nanoseconds. And the crystal it used, again, it's the ytterbium doped calcium fluoride. So this kind of crystal is considered as a suitable gain medium for femtosecond pulse generation, and it's a widely tunable CW laser. The substitution of the ytterbium ends for calcium, it leads to a rich multi-site structure result in broad absorption and emission bands. And ytterbium calcium fluoride comprises a long fluorence lifetime, which reduces the number of required pumping diodes in order to accumulate a certain amount of optical energy within the gain medium for a posted laser amplifier. And here we can see it's the experiment setup. So first we'll have a oscillator to generate our initial light. And for this paper research, it's the seed pulse will be at a pulse width of 85 femtosecond, and pulse energy of 1.3 nanojoule were generated, and it will then go into a pulse speaker, but I won't mention this today, and it will go into a grating structure to stretch the pulse, and it will get into a ytterbium doped glass preamplifier. This can consider as a first stage amplifier, and here is the second stage amplifier. So this second stage amplifier, the cavity is being shaped by M1. It's a plane diachronic mirror, and M2 is a concave concave mirror. The whole cavity length is about 95 centimeters, and the crystal we use is ytterbium doped calcium fluoride. And it's being pumped by a diode laser at 940 nanometer in wavelength. And the diode pump is being collimated by a cylindrical lens and was focused by a spherical lens, and it will focus into our crystal. And it will yielding a peak intensity of 83 kilowatts per centimeter square. And after a 32 round trip, a 17.3 millijoule of pulse energy will be determined. So figure 3a, this picture is the average output power. It's prior to the pulse amplification experiment, but it's they want to see about the tuning range of ytterbium calcium fluoride with an intracavity prism has been investigated. So corresponding to the broad emission spectrum of ytterbium calcium fluoride, a tuning range of 80 nanometer has been observed at maximum pump power. And the figure 3b is the input and output spectrum, which is determined by a fiber spectrometer and corresponds to the gain spectrum. After passing through the amplifier, the amplified pulse is being a little bit redshifted to 1032.5 nanometer in center wavelengths. And figure 4 is an experiment that in this paper they conduct two kinds of experiment. And this experiment is that they take out the structure and the preamplifier, so they just let in the initial light into the second stage of amplifier. So the our seed light into the amplifier is about 1045 nanometer in center wavelengths, and the output band amplified pulse will be at a bandwidth of 13.4 nanometer, and a total gain of 4 times 10 power 4 has been achieved. Figure 5 is just they put in different kinds of seed center wavelengths, and they measured out the bandwidth of it, the amplified bandwidth. And the second literature review will be similar to the first one. It's a broadband ytterbium calcium fluoride regenerative amplifier for millijoule range ultra short pulse amplification. So for this paper, the result is they give out a pulse up to 1.8 millijoule pulse energy at a repetition rate of 100 hertz, and it's pumped by a 10 watts continuous wave fiber, and it's at 978 nanometer. So this is the experimental setup of this laser system. So this M2 mirror and this M2 mirror shaped the whole cavity here, and as well the Huckel cell and thin film polarizer determined when will this laser pulse get out of this cavity. And the crystal they use is a 5 millimeter long crystal with 2.6 doping concentration, and the laser diode is 10 watts laser diode with center wavelength at 978 nanometer. Okay. And to optimize the overlap between the laser beam and the seed beam, they used a 200 micrometer diameter fiber and then collimated with a 250 millimeter focal length triplet here. And figure 2 is the average power of and output power energy. So the extracted energy will be 1.8 millijoule at 100 hertz repetition rate, and the average power will be 850 milliwatt at higher repetition rate. So the achieved extracted energy as high as 1.8 millijoule at 100 hertz repetition rate. It's because the Furnace lifetime of 2.4 milliseconds of the crystal explain a decrease of the output energy for a repetition rate higher than 300 Hz. And the maximum average output power is reached to 800 Hz. It's due to a complex interplay between storage time and amplification time. And figure 3 is it shows a significant influence of a polarized alignment. So we can see 3 kinds of spectrum, and the shape with a camel shape is possess a bandwidth of 16 nanometers. So theoretically, if your bandwidth is bigger than after compression in a chip pulse amplification, you have a better quality of it. So they used this spectrum here. And last, because the useful band for the amplification is around 1030 to 1050 nanometer in wavelengths, but the initial light from the oscillator it's centered at 1029 nanometers, but only a 6 nanometer broad spectrum. So they inject this oscillator to an undoped polarization maintaining large mode area fiber, DRMA. And this kind of fiber, they can it will happen a self-phase modulation. It leads to a considerable spectral broadening of this oscillator spectrum, which will becomes like this. And this spectrally broadened pulse will directly inject in the broadband regenerative amplifier and taking benefits of the stretching effects of the fiber. So the summary, both of these two papers report a regenerative amplifier design by using broadband and high energy regenerative amplifier based on a ytterbium doped calcium fluoride crystal. This laser material offers a good combination of high energy storing capacity together with broadband's gain spectrum. And both papers demonstrate a good potential of having a femtosecond pulse amplification, millijoule range of diode pumped ytterbium calcium fluoride regenerative amplifier. And number 4, my future work. So before we conduct the experiment of a sub-terawatt laser wave field acceleration system, we will need to first to construct a second stage laser amplifier. Since our first stage amplifier is finished, now we are constructing the second stage amplifier. And this second stage laser amplifier aims to amplify the laser pulse from our initial pulse energy from 40 nanojoule to 80 millijoule, and with a pulse duration of 50 femtoseconds. So a quick glimpse that this is my future work, and this figure is captured from the paper of multi-mega EV electron acceleration by sub-terawatt laser pulse. It's briefly speaking that there will be a hydrogen gas jet nozzle spouting a thin and high density of hydrogen gas, and the laser with only like 10 millijoules is focused on the point, and then a mega EV scale energy electron bunch are generated. This is my future work, so now I just can only explain this part here. Okay, and thank you for listening.一侧边的这个凯撒牌嘛，它是因为它的那个 broadband emission 跟它的 broadband 的 absorption 就是可以去达到我们想要的那个条件，所以最后他们就选用是用这种 crystal 去做我们的 second stage 的 amplifier。
为什么用 broadband？ 因为你进去这个到底要port单位。
对，我们有，但是也有先 stretch 我们的那个 port。对，它最后还是要符合那个。
为什么那个port？
应该是那个 gain saturation， 就是它的 Fourier lifetime 已经就是它的如果 repetition hertz 已经过多，它应该是每一发它会去带走太多，就是它没办法跟上。gain saturation 应该 pump 来的，它这个是对，它是 CW pump。那我读到的是它的，应该是它的 gain。但是因为它是写 Fourier lifetime 比较长，对，所以它掉下来它还没上去的时间，它就是太多 pulse 进来，因为它有 2.4 millisecond， 对 2.4 millisecond 很长的 lifetime Fourier lifetime， 所以它是应该是来不及。
所以这会限制会限制到大概。所以你的设计就是这样，设计到刚开始
可能
你们这样做开了，
我们最后的 repetition rate 里面不会到很高，100赫兹，对呀，大概100赫兹。
你也是要用CW。
我们最一开始的是 CW pump，